In 3.5, we'll talk about linear approximation and differentials. The first topic we'll focus on would be linear approximations. And basically what a linear approximation is if you're given a function that is a curve, if you zoom in toward any point on a graph, it's going to look like a line. And I'll show you a demonstration here in just a second. So if we have some given point, x sub 0, f of x sub 0, which this is just really x comma y, there could be a point that we want to approximate the value of. So what we're looking at here is if we're given the function f of x, which is right here, this is f of x, and this is our tangent line right here. If we can use a value, f of a, and approximate that value that is not on the curve, so you notice here there is a distance between the curve and the line. This looks like a huge value, but it's actually so small. This is just so zoomed in. We can use this line, L of x, which is the linear approximation, to approximate this value at x for f of x. So as I was saying before, if we have the function y is equal to x squared plus 1, so I put this into my calculator and I graphed it. If I just pick any point on here and I zoom in on it, so I'm going to zoom box, and I'm going to pick any point. We know that there's a curve. This is curved because it's a quadratic. And if I zoom in close enough on this, what's going to happen is it will look, if I zoom in on this point right here, zoom to right here, it starts to look like a line. The more I zoom in on it, it becomes linear. So if we're zooming in so close, we can actually use a linear approximation to figure out that value. So what we'll start off with is our point slope equation, which is y minus y sub 1 is equal to m times x minus x sub 1. And then what we want to do here, before you guys would just leave the equation like this. Now we want to solve for y. So that means we're going to add y sub 1 over here to the other side, which is y is equal to m times x minus x sub 1 plus y sub 1, meaning this is a numerical value. Okay, and what this is then is the linear or local linear approximation. So the standard equation for this is f of x is approximately equal to f of x sub 0, which is my y value, plus f prime of x sub 0, which is my slope, times x minus x sub 0. Okay, this is the same thing as this, except now what we're going to do is instead of having f of x, we're going to write it as a linearization, meaning the notation L of x. So you can see it like this, meaning it is m times x minus x sub 1 plus y sub 1, or if they use this notation, you would see it like this. F of x sub 0 plus f prime of x sub 0 times x minus x sub 0, which is L of x. I typically use this one because it's just a derivation of what we've already used. So when we are using linear approximation, we need to take a look at the two types of graphs. If this is my function f of x, and this is the tangent line at a given point A, then this is considered an overestimation. So all points will be above the curve, and this will occur when the graph of f of x is concaving down. That's a notation for concaving down, and the linearization is above the graph. So what you have here is L of x is greater than f of x. Okay? And this is when our function is concaving down. So the reason would be f is concaving down. So if you were asked to justify your answer. Okay, on the other hand, we would have an underestimation when the graph is concaving up CU, and the linearization is below the graph. So if this is f of x, this is my linear approximation, meaning my line that is tangent to the curve when x is equal to a. That means that L of x is less than f of x, and your reasoning or your justification would be f is concaving up. So here this is less than, and that would be your justification.